In this video, we're going to talk about mixtures and the scientific method. Let me share my PowerPoint with you. Last time we had discussed what a substance is, what matter is, and what an element and a compound are. And we talked about this difference between physical separation and chemical separation. So now we're going to go over here in this diagram and talk about mixtures. So mixtures are a combination of two or more pure substances. So we have two or more types of things inside of our mixture. So that might be like combining water with the gold or something, or combining water with salt. These are examples of mixtures. We're putting two things together. Now we have different types of mixtures. These are homogeneous and heterogeneous. So a homogeneous mixture is one where the components are distributed uniformly throughout the sample, and you can't really tell that there are different components inside of it just by visually looking. So things like gasoline are a homogeneous mixture. It just looks like a bunch of black goop to you, right? You wouldn't know that there's different types of hydrocarbons in there of different lengths unless you knew the chemical composition of the substance. Or things like apple cider vinegar is an example of a homogeneous mixture. There are different types of chemicals inside of there. There's water and your acid and other types of flavorings, but all we see is a brown liquid. So that's homogeneous to us. We can also call these mixtures solutions a lot of times whenever you're seeing these things mixed homogeneously together. So we often use this in the lab whenever we are dissolving solid chemicals into water. You can also have solid mixed with solid solutions. That's a little more complex of a topic, but you'll see this a lot in lab. You'll be making a lot of solutions in the lab. Okay, so then heterogeneous, which is still a mixture. It's still got two or more things mixed together. However, these components are not distributed uniformly throughout the substance. And so they might have different regions or distinct compositions that you can visually see. So something like oil and water, those separate, they don't stay together. It's still a mixture because, yeah, they're mixed together in the same container, but they are not evenly spread out. And you can see that distinction, so you really need to be able to see it. Salad dressing is a good example of a heterogeneous mixture as well. Okay. So let's talk about a couple of methods where you can separate out mixtures. So these are physical means of separation. One of these is centrifugation. So if you want to take a mixture that's homogeneous and make it where you can see all the different components, you can often run it through centrifugation. And what this is it's a device where you put test tubes of your samples in it, and it spins around really, really fast like this. And what that causes it to do is it causes gravity to pull on the substances in the mixture, which separates them out by size and how heavy they are. And so you can see an example of a scientist here who's run a sample through the centrifuge, and you can see the distinct different parts of the solution separated out. Another way that we can separate out mixtures is through this process called electrophoresis. If you do any work with biochemistry or maybe more molecular biology, you will probably use electrophoresis at some point. This is normally how we separate DNA, which is why it's an important technique. And what happens is you run a current through your mixture, which is usually like a sample of a bunch of different types of DNA. And these molecules, because DNA is a molecule, will separate out by size and their charge. And so we can see those mixtures being separated and identify specific pieces of DNA and molecules in particular. We also have filtration, which might be a good process for you to visualize since you might be more familiar with that. You can separate out gases or liquids by passing them through some kind of physical barrier. Something like a water filter is a filtration apparatus. You're pulling chlorine out of your water, so you're separating that substance from the other substance, right? And another, I think, important thing to realize here is when you pull chlorine out of the water, what you're doing is you're pulling one thing out, and then the resulting stuff that's left over is, if your filter is really good and it pulls out chlorine and everything else that's not water, then you're left with a pure substance that's just H2O. But if your filter is only pulling out chlorine and there's still a lot of other stuff in your water, you're left with a mixture still. So make sure that you understand that you can pull apart mixtures by physical means, but it doesn't necessarily mean that you're going to end up with a pure substance. You might just end up with a more refined mixture that has a little bit less of whatever you removed. So you can end up with a pure substance if you have a really good separation method, but if you don't, most of the time you're just going to get a more refined mixture. And then the last method I want to talk about is distillation. So distillation is something you might be familiar with in terms of making alcohol. So we make alcohol in distilleries, right? Drinking alcohol. And what this does is you take your alcohol mixed in water and you evaporate the alcohol off of it and catch it in another container. And so what that does is it concentrates the alcohol that you're catching, because alcohol boils before the water does. And so we can separate out these components. So ideally you should have alcohol and water separate into two mixtures, or separating out these mixtures. And so you're getting these different substances. We also saw this example with gasoline. So gasoline was undergoing that distillation process where it's heated up and the vapors are removed and isolated as they're evaporated. And that is the process of distillation. Okay, so here's a flow chart of all the matter stuff that we talked about for topic 1. So matter is an all-encompassing term, and if we can separate matter by physical processes, that determines whether it's a pure substance or a mixture. And inside of our pure substance, we've got different types of classifications. We've got elements and compounds. So if you can break it down by a chemical reaction, then it's going to be a compound. So we've got different types of elements from the periodic table of elements in there. And our elements are just pure elements straight from the periodic table. There's nothing else mixed in there and chemically bonded to it. Now, on the other hand, our mixtures, which are individual, which is a mixture of different types of compounds or different types of elements, different types of substances. We've got our homogeneous and our heterogeneous. So our homogeneous is something that looks uniform throughout, and you can't really tell it's a mixture by visually looking at it. That's usually a sign it's homogeneous. Heterogeneous is the other way around if you can't determine that it's uniform throughout. And these can be separated by physical processes, and you might take a mixture and separate it by physical processes into a more refined mixture. Or if you have a really, really good separation process, you might turn it into a pure substance, separate it into two pure substances, and be able to isolate those further if you wanted by a chemical reaction, say. Okay, here's a visualization of what these things look like, so you can kind of get it in your head on an atomic level. So for an example, helium is a gas. This is a picture of atoms of helium. This is a pure substance. It only has one thing from the periodic table in it, and therefore it is an element as well. This over here are molecules of carbon dioxide, which is also a gas. And this is a pure substance as well, because it only has one type of substance in it, but it's a compound because it's got different elements inside of it. It's got your carbon and your oxygen. And then on the far side, we have our mixtures of gases. This is a bunch of different molecules mixed together. This might be air, for example. Air is composed of like nitrogen, oxygen, argon, carbon dioxide, water vapor. It's got a lot of things in it. So that's a good example of mixtures of gases. And this is a homogeneous mixture in this picture here, because if it's a gas, we aren't going to be able to see the distinct components. I want to make one more distinction as well for terminology purposes of chemistry, and that's distinguishing between an element and an atom. So the smallest particle of an element that retains its chemical characteristics is that called an atom. That's what we call an atom. So it's the smallest particle that retains its chemical characteristics. So if you break down an atom further, what's going to happen is it doesn't have those chemical characteristics anymore. So that's why we call it that. All right. So inside of here, you can see our different atoms. This is a water molecule here. We've got an oxygen atom, which is the blue thing, and then we've got our hydrogen atoms, which are the green things. Now, this other definition here is on molecules. So a molecule is an assembly of two or more atoms that are held together in a characteristic pattern by chemical bonds. Cool. Okay, so water molecule, we stick our atoms together, right? But now let's look at oxygen. Oxygen gas is an element because it's only composed of oxygen. However, oxygen is composed of two atoms stuck together. So even though it's an element, it has two atoms inside of it, which makes it a molecule. It is a molecule, but not a compound, because it only has one type of atom inside of it. It is an element, but not a compound. Okay, so this has two atoms inside of it. It's an element. It is a substance. It is a molecule, but it is not a compound. The compound has to have more than one type of element inside of it for it to be classified as such. Okay, let's go into properties of matter. So let's talk about intensive and extensive properties. An intensive property is a property of a material that is independent of the amount of substance present. So things like color, luster, melting point, boiling point. No matter how much water you have, it will always boil at 100 degrees Celsius. It doesn't matter. Hardness, density, these are things that don't change no matter how much you have of it. On the other hand, extensive property is one that varies with the amount of substance you have present. So things like mass, how much something weighs, the volume, these are things that change when you have different amounts of it present. Physical and chemical properties. So a physical property is a property of a substance that can be observed without changing it into another substance. So it's pretty much without undergoing a chemical reaction, what kinds of things you can observe about the material. So I keep using gold, so we're like melting gold in a pot here. Things like luster, hardness, color, state, melting point, boiling point. Again, these things don't change no matter how much you have of the substance, and they aren't changing into another substance. It's still gold no matter whether you've melted it or it's a solid. Same with water. Think about water. H2O. It's still H2O no matter if you freeze it or melt it or boil it. At the end of the day, it's still an H2O molecule. And so that's a physical property. Chemical properties are properties of a substance that are only observed when you react it with another one. So things like flammability or maybe oxidation, how oxidizing a material is, you might have heard that one as well. Oxidizing usually has to do with its explosiveness a lot of the times. So flammability, we won't see if something burns unless you light it on fire, right? You have to start the reaction somehow in order to observe that chemical property. The last thing I want to talk about is the scientific method. So this is a process by which scientists observe phenomenon and make educated experiments around them in order to determine theories and establish scientific facts and knowledge. So we do this primarily through what's called a hypothesis when using the scientific method. So this is pretty much an educated guess. So it's a tentative and testable explanation for an observation or series of observations. So you look at something and you make an educated guess about it, and then it's tested. And if it's tested over and over again, and you get the same results, and you build a body of knowledge, what this allows you to do is to form a scientific theory about this body of knowledge. So a scientific theory is a general explanation of a widely observed phenomenon that's been tested via hypotheses and validated over and over again. It's very repeatable. So here's what scientific method looks like in practice. So first you observe a natural phenomenon. You might see something interesting and be like, I wonder how that works. All right. And so you observe it and you make an educated guess about how it's working. And then you set about to test your educated guess. So you're testing your hypothesis by designing an experiment and performing it. And then what you're going to do after that is you're going to get some results. And you're going to want to look at those and see if they prove your hypothesis or disprove your hypothesis. And what you might end up doing is after that, finding out that you need to go back and fix your experiment because your experiment didn't give you the results you wanted, or maybe you need to go back and revise your hypothesis and test that and see if you can prove that point. So this is an ongoing process. You might even need to go back and re-observe the natural phenomenon to look for something maybe you didn't see the first time. And so it's kind of like a feedback loop. You're looking for something and then going back and modifying it, trying this new thing and testing and testing and testing. And then eventually, what's supposed to happen is you will test your hypothesis, and you'll be able to prove your hypothesis after a while. And more people will try your experiment and test it and test it and test it until eventually we have a large enough body of knowledge that we can establish a theory. Because this point that has been made, maybe you made it, maybe you're a famous scientist, has been validated by others, and now we can establish a theory about it, and we can say this is how the natural world works because we've tested these different things and we do have proof for these things. So here's an example of this evolution of knowledge of the scientific method and practice. So again, like I said, things have to be repeatable in order for us to be able to build scientific knowledge. This is the evolution of the discovery of DNA. So if we look here, it started all back in 1865 when Mendel observed DNA in action and was looking at the heredity patterns in pea plants. And so he's observing a natural phenomenon. And there's more and more observations that happen over the timeline. They're doing testing with X-rays in order to look at how DNA works and how chromosomes work. Somebody here proposes what a chromosome is, and then they go and test it to make sure that that's exactly what it is. And then over time, that eventually leads to Hershey and Chase in 1952 proving that DNA is responsible for heredity. So we're seeing the scientific method, people observing stuff, testing it, other people testing it, until eventually we come up with a scientific theory in order to build scientific knowledge. Okay, so that's the end of topic 1. Let me know if you have any questions. You can always type those in the shared Google Doc below this video.